Happy Friday, everyone. This is Friday, April 24th, and this is episode 20 of our Google Hangouts and podcast on all things Doxis. I'm Brady Volpe, founder of the Volpe firm and Nimble This. Today for our show, we have a fantastic guest for us, Ron Hranac. He's quite well known. He's an RF whisperer and technical lead at Cisco Systems. Ron, absolutely great to have you with us.
Well, thanks, Brady. Nice to be here. Haven't been called an RF whisperer before, but I think that beats an old cable guy.
Yeah. Well, it's you're very well known in the industry. Also, I know that you're just coming back from, or you were in London very recently, where you received the 2016 Tom Hall Award for services to the broadband industry, and I want to congratulate you for that award, and like it if possible, if you can just tell us a little bit about it and give us background on that.
Well, thanks for the kind words, Brady. The award is a pretty humbling recognition. Now, many operators in the U.S. may not be familiar with Tom Hall, but he has been in the or had been in the cable industry for decades. He was involved very very early on with the UK SCTE, and back in the 1940s, the organization was called the Society of Relay Engineers, and in those days they provided radio station services via wired networks, and then of course later it transitioned into video. And he was involved with the UK SCTE from the mid 1940s until his passing in 2002 at just shy of his 90th birthday, and very very well known in the engineering community and the European cable industry, and in particular in the UK cable industry. I'm very fortunate that my wife and I became good friends with Tom and his wife back in the late 80s and early 90s, so it was truly an honor to receive an award that's named after Tom.
So that's fantastic. I'm just curious. Does this mean you're going to have yet one more badge on at the SCT Expo, or your long list of badges?
No, unfortunately not. The UK SCTE is a different organization from the SCTE that most operators are familiar with here in the US. So no more ribbons for the badge for that one.
Okay.
Not that I'm.
Now that's good. It's hard to keep up with you on that side. John, I would like to introduce our third guest, John Downey. You're our typical stay at the podcast, but don't call you late for dinner, but glad you're able to make it here.
I was out getting my new ribbons for Ron.
Yeah. All right, John, well, welcome. Ron, you're going to be doing a presentation today on really fundamental RF measurements, and I think this is really quite important for the industry, primarily because we have, so RF is so important for DOCSIS communications, as we all discuss so frequently. If the physical layer is not working, then DOCSIS is pretty much not going to be working. So this presentation today that Ron's going to be going through, and we'll be discussing it during the presentation, is kind of really focused on the basics of RF and how it works. So Ron, I understand you have a hard stop at the top of the hour, so I'd like to really start letting you go ahead and start with the presentation. So take it away,
All right.
Ron.
Thanks, Brady, and welcome, John. I'm going to click share screen here, and we'll bring up a presentation that is called "What is Signal Level?" This is an abbreviated version of a PowerPoint presentation that I put together several years ago and have used in a variety of venues over the years. The longer version gets into really the nuts and bolts of electricity and electronics and current and voltage, power, and whatnot. This is a little bit less detailed than that, primarily because the other one takes about 3 hours to go through, and this one takes a little bit less time. So let's start out with the obvious question, and that is what is signal level? What is it that we measure when we're measuring signal level? Because I think most people who've worked in the industry for any length of time have probably measured signal level in a head end, or the input or output of an amplifier, or the input to a cable modem in a customer's house. But how many people have actually stopped to wonder, well, what is it that's being measured? Well, the simplest explanation is that we're measuring the amplitude of a signal or signals, but what does that mean? Well, let's take a peek at something many of us are familiar with, and that's an unmodulated RF signal, or CW carrier, which is an abbreviation for continuous wave. That can be thought of as a high frequency, and in this case I don't mean the 3 megahertz to 30 megahertz high frequency spectrum, but just a high frequency sinusoidal alternating current waveform, and that's an important point. The frequency of that signal can be several kilohertz, several megahertz. It can be in the gigahertz or gigahertz, terahertz range. But the key point here is that it is an alternating current waveform, and we can express RF signal level in a whole bunch of different ways. In terms of voltage, in which case we use volts to describe the signal level. We can measure it in terms of current, where we use amperes to describe that level, or we can measure it in terms of power, where we use watts to describe the level or amplitude of the RF signal. I want to start with an example that shows measuring signal level in a cable network using voltages. And right away people might think, well, hey, no problem, because we use this thing called dBmV, or decibel millivolts, so we're already measuring voltages. And I'm going to step back from that even and look at a few examples. Let's
Ron, can I ask a question real quick?
Sorry?
Can you hear me okay?
Yeah, I can hear you. You're making a lot of noise, John.
Sorry, so I have a question that always comes up, and Brady can attest. This is how I like to interject on him all the time. I always have questions that come up, and people that don't really know RF, the ins and outs, might say, and I know the answer to this, but I want you to say it. What is the width of a CW carrier? Or why do you see a CW carrier on a spectrum analyzer seem to have a certain amount of width?
Let's hold that question for just a bit, because on a subsequent slide I've got a spectrum analyzer screenshot of a CW carrier, and that's a perfect question that'll go along with that.
Perfect, thank you.
Okay. Yeah. Let's take a look first at a variety of signal levels that might exist in a cable network, but from the perspective of voltage. Now remember, we're dealing with a sinusoidal based signal. It's an alternating current waveform, so we're going to use a metric called root mean square to describe the alternating current voltage, and we do that because RMS, or root mean square, is one of many ways to measure a sinusoidal waveform. The graphic at the bottom of the screen here shows what a sine wave would look like on, say, an oscilloscope in the time domain, where in the vertical axis we have amplitude and in the horizontal axis we have time. And looking at this sine wave, we can express its amplitude in terms of a peak-to-peak value, a peak value, an RMS or root mean square value, or an average value, which I don't show on this particular slide, but these are all different ways to do this. But we use RMS because with alternating current waveforms, an RMS voltage for that alternating current waveform will give us an equivalent value to what we would get if we were measuring the same DC voltage. So that's a primary reason we use RMS here. But some typical levels that you might see from a voltage perspective in a cable network is say 100 millivolts per channel at the output of a line extender, maybe a bit over 7 millivolts at the output of a tap spigot. Hey, John, are you moving furniture or something in there? It sounds like it.
I think I thought I was muted.
No, I think your headset isn't working, John. I think we're picking up the computer. Your computer is picking up all the background noise.
I think he's just moving furniture or something. Rearranging furniture there in his office. Anyway, the input to a TV set or cable modem or set-top box might be 1 millivolt, and the input to a line extender in the outside plant, again, these are all per channel levels, might be 10 millivolts. Now you look at this and say, well, wait a minute, we don't measure RF levels this way, and that's right, we don't. It's kind of a cumbersome, clunky way to do it. So a better way to do it is to use the decibel. Now in this case, a signal level in millivolts can be expressed in decibels as a ratio of that signal level to 1 millivolt across a 75 ohm impedance, where 1 millivolt across 75 ohms is equal to a power of 13.3 nanowatts. We call this, as I mentioned earlier, dBmV, or decibel millivolts. And here's another important point to keep in mind. dBmV is a unit of power expressed in terms of voltage. Most people think, well, wait a minute, I see this MV abbreviation tacked onto the dB part, and that means we're measuring voltage, right? Well, the decibel is a way to express power, and in this case, or more specifically, the ratio of two power levels. In this case, we're measuring power, but in terms of voltage, and we'll see more about this a little bit later on. Mathematically, then, dBmV is equal to 20 times the base 10 logarithm of whatever the value in millivolts is, divided by 1 millivolt. So if we take a look at an example of 10 millivolts RMS, and we convert that to dBmV, what's the answer? Well, dBmV in this case would then be equal to 20 times the base 10 logarithm of 10 millivolts divided by 1 millivolt, and as you work through the equation here, the answer we get is 20 dBmV for 10 millivolts RMS in a 75 ohm impedance. So now if we apply that same math to the previous examples that I showed you, the per channel line extender output, instead of calling it 100 millivolts, we can call it 40 dBmV. At the per channel signal level at a tap port spigot, instead of a bit over 7 millivolts, is now 17 dBmV. And the input to a cable-ready TV or a cable modem or set-top box, instead of 1 millivolt, is 0 dBmV. And the input to a line extender on a per channel basis, instead of calling it 10 millivolts, is 20 dBmV.
So Ron, I have a quick question for you. When we're talking about these voltages now of like 100 millivolts, these sound like incredibly small levels. I mean, I can buy a 9-volt battery, and that's so much more voltage than 100 millivolts. So these signals that we're dealing with on the cable plant, they seem so incredibly small. How do we understand it? You know, why are they so small?
Well, when we're dealing with RF or any alternating current waveform, it can be any number of signal levels in terms of voltage, but the reality is the signal levels in our cable networks are quite small. In order to transport signal levels at much higher levels, let's say 9 volts or something, we would need humongous amplifiers that would consume incredible amounts of power from the electrical power company to even operate. So you can imagine, instead of a few millivolts for a signal level on a channel, if we were talking about something up in the range of a volt, that's going to be a substantial amount of RF signal energy. At that point, we're talking signal levels that would exceed the capability of our amplifiers, our passives, and indeed the signal levels involved there could even cause permanent physical damage to those components. And the reality is, if we go back to what it takes to produce a decent quality picture, 1 millivolt for an analog TV channel signal level is sufficient to produce a noise-free picture on a typical TV set. So there's no reason to carry much higher signal levels than what we do.
Great, thanks, Ron.
Sure. Now, speaking of those signal levels, the examples I gave previously showed an unmodulated carrier, a continuous wave or CW carrier. Where things get really interesting is when the carrier is modulated. So what the heck happens when the carrier is amplitude modulated? And if the example I showed earlier of a CW carrier, just a sinusoidal unmodulated signal, it was fairly easy to describe where to measure that signal. But when the envelope of the signal is changing because it has been modulated, where do we make the measurement? It's varying continuously over time, and it makes it much more difficult to actually to measure that. So where the heck do we measure it? Well, a good place to start is with a metric called peak envelope power. Many of you may not be familiar with this term, but it has been around for a long time and applies very nicely to the way we measure signal levels in our cable networks. The peak envelope power is abbreviated PEP, and by definition is the average power in watts during one cycle at the crest of the modulation envelope. And now right away I've introduced some new terms that may be a little bit confusing, or certainly not necessarily real familiar to a lot of people. But here again, we need to look at our sinusoidal alternating current waveform in the time domain, at least to get a grasp on the concept that I'm trying to explain here. So if we draw some red squiggly lines to represent the envelope, that is the modulation envelope, in this case of an amplitude modulated carrier, then we can see that the crest of the modulation envelope is at the peaks as shown on this graphic, and then of course the varying envelope represents the modulation that's being conveyed by the signal. So what we want to do then is determine the average power of one cycle at the crest of that modulation envelope. And then I'll show you how we apply that to an analog TV channel's visual carrier here in just a bit. So let's start with this by looking at another metric that many of us are not necessarily familiar with, and that's peak envelope voltage. So in this case, it's kind of a bit of a subtle variation of the example I showed earlier, where we can express the amplitude of a sinusoidal waveform in the time domain in terms of peak to peak or RMS or average values. In this case, we're looking at a peak envelope value or peak envelope voltage, which goes in this case from the center of the waveform to the peak, that is the highest peak of that waveform. Now for this example, let's assume that the peak envelope voltage is shown is a bit over 14 millivolts, so 14.14 millivolts. What we do, and pardon me, I'm just getting over the tail end of a cold, what we do is plug it into this formula, and to determine peak envelope power, we take the peak envelope voltage, multiply it by 0.707, square that value, and then divide by resistance, which in this case is the impedance of the network, or 75 ohms. So if we plug in the 14.14 millivolts as a voltage, that's 0.01414 volt. Multiply it by 0.707, square the value, divide by 75 ohms, and what we get is 1.33 microwatt, which is a really, really low power. But that's the average power during each cycle at the crest of the modulation envelope. And as you look at the graphic at the bottom of the slide, the sinusoidal waveform that I've highlighted in red represents the cycle that occurs during the crest of the modulation envelope. And in this case, the power of one cycle during the modulation crest is 1.33 microwatts.
So you're just looking for the highest portion of the sine wave. You're looking for the peak sine signal throughout this whole carrier. Is that correct?
That's right, and I'm going to show why that's important in just a moment when we start looking at an analog TV channel visual carrier, because there is a part of that that is a peak, and that's what we're interested in measuring, and you'll see how all this comes together here in just a moment. Now, much like using, say, voltage or amperes or some other metric to express amplitude in a signal of a signal in a cable network, it would just be cumbersome as all get out to use peak envelope power to express signal levels in a cable network. Can you imagine saying, well, the line extender's per channel input signal level is 0.000000133 watt peak envelope power? Well, we're not going to do that either. That's just simply too clunky to deal with. But recall that, as I mentioned earlier, peak envelope power is the average power of one cycle during the crest of the modulation envelope. Now, in the case of an analog TV channel's visual carrier, the crest of the modulation envelope occurs during sync pulses. And then so the sync pulses represent the carrier's maximum power. And the interesting thing is the amplitude of the sync pulses does not change even as the picture content varies over time.
Right. If it's a black picture or a white picture, the sync is going to be the same, even though the power changes quite a bit from a dark to a white picture.
What's kind of a fun little experiment, if you have a thermocouple type power meter, hook the thing up to the output of a head-end modulator that just has one analog TV channel, and as the picture content varies, the average power of that RF signal will also vary. But what's not varying is the peak envelope power, which is the average power of one cycle during the modulation crest, which happens to be during the periods of time when the sync pulses are present. So that stays constant, and that becomes our reference for a modulated analog TV channel. visual carrier signal level. So if we assume then our 75 ohm cable network impedance, that 0.000000133 watt is equal to 10 millivolts RMS, or 20 dBmV, going back to the formula that I showed earlier. So here, and this is another key point to remember, 20 dBmV is the RMS value of the instantaneous sync peaks. It's a unit of power, which in this case is 0.0000133 watt, PEP, expressed in terms of voltage. So this is where the dBmV comes from, and what the definition of dBmV is all about. Now,
yeah,
this
so
is
you kind of lost me on that last bullet point there. The plus 20 dBmV is the RMS value. Because isn't that going to change on? Is that based on what reference?
The sync pulses.
Yeah, but if your plant is balanced at a different level, or is this has to be referenced to something, right?
Well, it's always referenced to 1 millivolt across the 75 ohm impedance. That's what dBmV is. It's always relative to 1 millivolt across a 75 ohm impedance, and that one millivolt is 1.3 or is 13.33 nanowatts. So that's our reference.
Okay.
Now this isn't saying that the 20 dBmV is a reference. Not at all. I'm just using 20 dBmV as an example in this particular instance. But what we're saying is that the dBmV is a unit of power. Now in this case, 20 dBmV happens to, in a 75 ohm impedance, happens to equal 0.0000133 watt PEP. But we're using dBmV as a unit of power expressed in terms of voltage.
Right. Going back to the previous point where it's 10 millivolts, then it's 20 dBmV. I understand that now.
That's right. That's right. So it's all related. Now let's take a look at an RF signal. This is a screenshot from an oscilloscope, and in this case, I set a visual carrier from a modulator to 40 dBmV, and plugged the output of the modulator with the oral carrier disabled into a wide bandwidth oscilloscope. It was properly terminated with 75 ohms on the input. And what that oscilloscope lets us do is measure the amplitude of that unmodulated carrier, which is 100 millivolts RMS, or 40 dBmV. As soon as we apply modulation, in the case of NTSC, it's negative AM, negative amplitude modulation. The peak-to-peak value of the carrier does not change. That is when we reference the sync tips. So the amplitude of the sync tips is the same as the amplitude of the unmodulated carrier. So as the picture content gets brighter, the average power of this carrier will decrease, but the peak envelope power remains the same, because remember, the peak envelope power is the average power of one cycle during the modulation crest. Well, the modulation crest, which happens to coincide with the sync pulses in an NTSC analog visual carrier, that doesn't change. So in this case, the amplitude during the sync pulses is 100 millivolts RMS, or 40 dBmV. And when we use a signal level meter or some other instrument to measure the amplitude of a visual carrier on an analog TV channel, that's what we're measuring. We're measuring the amplitude of the sync pulses, or the amplitude of the signal during the sync pulses.
Okay, so the image on the left-hand side, that has no modulation on it, so it's just like a sine wave at
a
very
wave,
high frequency.
Right, it's just a sine wave, and I forget which. I think this was channel 2 or channel 4, somewhere in there. It was in the low VHF range, plugged into an oscilloscope. Now, if we set the horizontal scale on the oscilloscope to a different value, then you'd see the individual sinusoidal waveform component of that. But that's just an unmodulated sinusoidal signal on the left. And on the right, there it is with modulation applied. And note that the peak-to-peak value is 282 and change millivolts peak-to-peak. The RMS, the peak value would be half of that, so about 141 millivolts peak. But what we're interested in is RMS, because when talking about alternating current waveform levels, we express them in terms of an RMS voltage. And the same is true if you measure the voltage on a wall outlet, AC wall outlet. When we use a voltmeter to measure that, we're measuring the root mean square value of that that voltage coming out of the wall outlet are around 117 to 120 volts. That is a root mean square value.
Right. So peak voltage goes down, but RMS stays the same.
That's right. Well, here you can see it here. It's the RMS voltage during sync pulses that's 100 millivolts. If you look at the modulated waveform during another part of the signal when sync pulses aren't present, then the RMS voltage would of course be less. But during the sync pulses, because they don't change, we make our measurement of the signal level because that's a constant that we can refer to all the time.
So because we do negative modulation, a darker picture would actually be higher power. Is that correct?
That's right. And a wider picture or a brighter picture would be less power.
I always found that interesting. Me and Brady both worked at Seacor Electronics, and way back in the day, we used to do distortion testing with the Dix-Hills matrix. And basically, you were always did the testing with CW carriers. So we always knew that whatever performance we got with CW testing, we should get better performance when you actually have modulated carriers because they would be negative modulated.
That's right. And the reason is that the average power of that visual carrier decreases and varies when modulation is present, but the peak envelope power remains fixed. The neat thing about that is when it comes to characterizing distortion performance in a network with a matrix generator, or what used to be called the Dix-Hill generator, the CW carrier produces the worst case results, which is what you want to know. In an operating cable network with modulation applied, you actually buy a little bit of we'll call it visual or visible improvement because of that variation in the average power of the visual carrier.
Cool, thank you.
Now let's go back to your question, John, earlier about the width of a CW carrier. This is a CW carrier in the frequency domain. That is as viewed on a spectrum analyzer. So in this case, the vertical axis is amplitude, and the horizontal axis is in frequency. Now, on an oscilloscope, this same signal in the time domain looks like the screenshot on the right. And if we change the horizontal time adjustment on the oscilloscope, then we can see this. We can see that that signal as a sine wave. But back to your question, John, about the width of a CW carrier. A CW carrier doesn't have any width, and that surprises a lot of people because they look at a spectrum analyzer and say, well, wait a minute, I see it right there. It's got width on the screen. That's true. Now, there are a couple things that contribute to that. One of them is the filters in the spectrum analyzer, the IF filters, or resolution bandwidth filters. The other thing is we can't generate a perfect CW carrier. There will always be some power supply components in it, some hum, a little bit of hum in there that will modulate that carrier slightly. It's probably pretty low, but that will be there. The signal source itself is not a perfect signal source, so there's going to be a little bit of what we call residual FM. That is, the signal is going to be kind of jiggling back and forth a little bit, very, very slightly, hopefully, and generating, there'll be some variations in phase of that signal too. So we'll see a little bit of width that way, but it tends to be pretty small. But by and large, what's seen on a spectrum analyzer, as far as what we would call the width of that CW or unmodulated carrier, is really mostly an artifact of the test equipment itself. It's a function of the filters that are used. If you change the resolution bandwidth setting to a wider value, such as 1 megahertz or 3 megahertz, the carrier will appear to get wider. As you reduce the resolution bandwidth setting, which switches in a narrower bandwidth IF filter, then the apparent width of that CW carrier will also decrease. So a lot of that's really related to the display artifact of the spectrum analyzer, and then there'll still be some actual width to it in the spectrum because of some minor imperfections in the generation of that carrier. Does that answer the question, John?
Definitely. I mean, that's what I say. It's like an optical illusion. I mean, you're basically seeing the RBW filter response.
That's it.
So a typical default RBW would be maybe, 300 kilohertz? So right there, you might assume the CW is 300 kilohertz wide, but it's really the filter scanning across the screen, and you're seeing the filter, the filter response.
Yeah, in this case, the RBW is set to 100 kilohertz, and if it were changed to 300 kilohertz, the width of the CW carrier would increase on the display. Okay, now let's see what happens when we apply modulation. And in this case, the assumption is that the aural carrier is disabled. So we see the visual carrier at the center of the screen, and then a bit to the right of that we see the color subcarrier. And that's in the frequency domain. And in the time domain, it looks like the oscilloscope screenshot on the right, which is the screenshot that was shown a little bit earlier. But these two are the same signal. Just one in the frequency domain on a spectrum analyzer, and the other in the time domain on an oscilloscope. So I've talked about the level of an analog TV channel as being the peak envelope power of its visual carrier, but we use dBmV to state that as that power in terms of voltage. And it's pretty straightforward when measuring the signal level of an analog TV channel's visual carrier, but things get a little bit more interesting when we start measuring digital signals, which technically are analog signals.
Nah, they're all digital, Ron.
Analog RF signals. Anyway, when we're measuring the level of an analog signal, we're not measuring its peak envelope power because there's both negative and positive modulation on a QAM signal. So we do measure the average power, and that's called digital channel power or digital signal power. Nice thing is that most field instruments used by technical staff in the cable industry support the ability to measure digital channel power of our QAM signals that we carry in our cable networks. And typically the way they do it is to measure the level at several points across the bandwidth of that, what we call the haystack, the QAM haystack, and then integrate those results to produce the average power of the entire haystack over the occupied bandwidth. Another way you could do it is to use a thermocouple power meter. As long as you had just one QAM signal coming out of a QAM modulator, hook that up to a thermocouple power meter, and it would measure the average power of the QAM haystack. And the answer that produces would be very close to the answer produced by today's test equipment, which makes it very, very convenient, because when digital signals first started being deployed on cable networks, the instruments that were in use didn't support measurement of the signal level of a QAM signal, because it's noise-like. It was really difficult to accurately measure, and a lot of people weren't familiar with how to use a spectrum analyzer to properly set that signal level. Excuse me. So here's a QAM signal in the frequency domain, and here we can see its display of amplitude in the vertical axis and frequency in the horizontal axis. And in this case, it's a 6 megahertz wide QAM signal. It's called a single carrier QAM signal, or SC QAM. That terminology has been adopted since the introduction of DOCSIS 3.1, which brought us, or is bringing us, OFDM, orthogonal frequency division multiplexing. So to differentiate between an OFDM signal and our legacy QAM signals, we call these legacy QAM signals SC QAM, or single carrier QAM. Here's what one looks like on an oscilloscope. I would suspect that most people have never looked at a QAM signal in the time domain, but this is what it looks like. And to produce this, I took the output of a CMTS configured for single channel operation, plugged it into a high bandwidth oscilloscope properly terminated in 75 ohms, and then tweaked the time per division setting, which affects what's displayed in the horizontal axis. And here you can see a sinusoidal waveform that is varying in both amplitude and phase, which is what a QAM signal does. So this is a really good example of a QAM signal in the frequency domain on the left and in the time domain on the right.
Yeah, Ron, that is actually a really good capture that you have of a QAM signal converted into the time domain. So if anyone, a lot of our listeners catch this on iTunes or listen to these on audio-only podcasts, I'd highly recommend if I tell so many people the QAM channels are made up of sinusoidal signals with different amplitudes and different phases. And when I draw this or try to do it on PowerPoint, it never looks as good as this illustration that Ron has in his PowerPoint slide right now, because it's captured with a high-speed oscilloscope. So I would highly recommend anyone who's interested in really seeing what a 64 QAM signal looks like in a time domain. This really illustrates that it's not a digital signal. It's truly an analog signal with different amplitude sine waves, different amplitude voltages, and changing phases. It's just so complex looking, but this really truly shows you that it is indeed an analog signal.
Yes, and there it is. All right, now let's take a look at a spectrum analyzer screenshot that shows both what we call analog.
Can you hear me okay?
And QAM signals. John, did you have a question?
Can you go back a slide? And then you and I have had this discussion with someone else recently about the carrier frequency for a QAM. Is it there? Is it not there? Where is it?
Well, let's define what a QAM signal is. It is a double sideband suppressed carrier RF signal. What that means is if you look on a spectrum analyzer display like you see on the left, you don't see a carrier per se sticking up. This is there is a suppressed carrier in the center of the channel, but it's 40, 50 dB down, basically down at the noise floor, because in the modulation process, the carrier is suppressed, and all that's left are the upper and lower sideband information. Of course, it's filtered to give us this shape in the frequency domain, but we can define a QAM signal in a number of ways. Some cable operators like to call a QAM signal by its CEA channel number. Now, we used to call it EIA channels, but the reality is the EIA channel plan hasn't existed for over a decade or more, probably 15 years. But it is the CEA channel plan, and I think that name just changed recently too. And I can't remember what even the newest one is, but we'll call it the CEA channel plan. So we'll call it a CEA channel number, like channel 118 or channel 108 or something. Another way it can be described is by center frequency, which happens to be where the suppressed carrier is. For example, for channel 2, the center of channel 2 is 57 megahertz, so we might call that QAM signal, well, that's 57 megahertz, and that's fine. So we can call that QAM signal either channel 2, or we can call it 57 megahertz, in that case referencing the center of the channel and also the frequency of the suppressed carrier. Okay, now here's a spectrum analyzer screenshot that shows both analog TV channels and QAM signals in the same display. And this was something I snapped in an operating cable network. Just took a spectrum analyzer, connected it to the subscriber drop, and tuned to a part of the spectrum where both the NTSC analog channels were present and the QAM channels were also present. Now there's an interesting point that I want to make here too, and this is especially important because it's fairly easy to get this wrong. And when cable operators carry a QAM signal, typically the average power of the QAM signal is set several dB below the peak envelope power of the visual carrier. For 256 QAM, the channel power is typically set 5 or 6 dB below the amplitude of the visual carrier, or the peak envelope power of the visual carrier, and 64 QAM typically set 10 dB down. But as you look at this spectrum analyzer screenshot, it looks like the top of the QAM haystacks is 14, 15 dB below the level of the visual carriers. Well, that's misleading because, and I like John's use of the term optical illusion, because that's kind of what we're seeing here. The height of the displayed noise floor and the height of the QAM haystacks will vary as the spectrum analyzer's resolution bandwidth control is changed. And that's because the QAM signals and, of course, the noise floor are noise-like signals. So as we change the resolution bandwidth on the spectrum analyzer, the apparent height of those haystacks will change, even though the actual power is fixed. In this particular example, the QAM haystacks actually are set 6 dB below the amplitude of the visual carriers. Now, in this case, the resolution bandwidth is 300 kilohertz. So they appear to be 13 or 14 dB lower, maybe 15 dB lower than the amplitude of the visual carriers, but in fact they're 6 dB down. If we could change the resolution bandwidth to 6 megahertz, which of course doesn't exist on the spectrum analyzer, this particular one I think peaked out at 3 megahertz. But if we were able to increase the resolution bandwidth to 6 megahertz, then the QAM haystacks would in fact show up as 6 dB lower in amplitude than the amplitude of the visual carriers. The visual carriers and oral carriers on the analog TV channels would not change. Those amplitudes would stay the same as the resolution bandwidth change. But noise and noise-like signals will change in amplitude on the display when the RBW is tweaked. So we have to keep that in mind. Now, certainly one can apply all kinds of correction factors, but it's just a lot easier to use modern test equipment that has a digital channel power function, and the instrument does that measurement for you, and all you have to do is measure the visual carrier, measure the digital channel power of the QAM signal, and then set it to be 6 dB down, or ensure that it is 6 dB down from the visual carrier levels. All right, so let's wrap the formal part of this up, and then we can have some open-ended discussion here. Signal level is the amplitude of a signal, but in particular the RF power of that signal. The signal level in a cable network is expressed in dBmV, that's decibel millivolts, not dB. And I know I'm guilty of this, and I think most of us are, of referring to signal level in dB, and that's technically wrong. We can use dB to express gain, loss, attenuation, return loss, structural return loss, isolation, carrier to noise ratio, signal to noise ratio, MER or modulation error ratio. But when it comes to signal level, it's dBmV. And remember, dBmV is a unit of power expressed in terms of voltage. So when we measure the signal level of an analog TV channel's visual carrier, we are measuring its peak envelope power. And when we measure the power or signal level of a QAM signal, we are measuring its average power. And those are also a couple important takeaways from today's presentation. So digital channel power or digital signal power for our QAM signals. Okay, that's that particular presentation. Any questions?
No, that was really some great material you covered there, Ron. Very nice.
Is this one showing up okay, Brady?
Yeah. Yeah.
Okay. This is another screenshot of the amplitude, or sorry, the frequency and time domain of a QAM signal. This is a 64 QAM signal on the right, and on the oscilloscope display on the right, you can see where the time per division settings for the horizontal axis has been changed, so that you can really see the sinusoidal component of that QAM signal. But note the variations in amplitude, and particularly in the center of the screen, you can see the phase shift right there. It's a very, very obvious phase change. There's also one over toward the right edge of the screen, and if you could visualize this on a constellation display, the portion of the sinusoidal waveform on the left, as an example, might represent a couple symbols in the upper right quadrant of a constellation display, and then that phase shift we see in the center of the screen would be not quite 180 degrees, but it would basically go to the opposite quadrant, down in the lower part of the constellation display, to represent a couple different symbol points on the display. But the key here, and Brady made this point earlier, the QAM signals are analog signals, and you can see it very, very clearly here that it's an analog sinusoidal signal whose amplitude and phase varies to represent those what we call symbols, or groups of ones and zeros.
Yeah, no, that's excellent to show that, because sometimes it's important to have people really understand that when we send QAM signals, the fact that they are analog signals means that they're super prone to be impacted by any type of RF impairments we have in the plant, and that's why the higher the order modulation QAM, going from 64 QAM to 256 QAM, those RF amplitude variations that you're showing, the change in phase, there's going to be more of those, and then those become more suspect to impairments from RF. That's why we have bit errors, code word error, uncorrectable code word errors, MER goes down, and it's still inherently an analog signal that we're transmitting.
That's right. That's right. Well, hopefully this presentation has shed a little bit of light on some of the fundamentals of the RF signals in our cable networks. It's kind of a fun subject, because most of us take for granted the idea of measuring RF signal levels. Well, all right, well, never really stop to think, what is it that we're measuring? And hopefully this has communicated the point or points that when we measure signal level, we're measuring power. We're measuring the RF power of those signals. And for analog TV channels, typically when we talk about signal level, it's almost always referring to the signal level of the visual carrier. Now, certainly it can refer to the oral carrier, but more often than not, we're talking about the visual carrier, and that's the peak envelope power. And then for our QAM signals, we're measuring the average power or the digital channel power of that signal. But we're measuring analog RF signals here, and I have fun with this at SCTE and other seminars where I'll ask people in the audience, how many of you are carrying digital signals on your networks? Because everybody raises their hand. I say, well, no, you're not. You're not carrying digital signals on your network. You're carrying analog RF signals on your network. Those analog RF signals may represent digital data, but they're actually analog RF signals.
Semantics.
Semantics. That's right.
Yeah,
I'm a semantic kind of guy.
Yeah. I have another example. What about optics, like optical level measurements, reference to microwatt, right? So we use the term dB mu instead of dB mu W.
Well, optics are that's dBm, right?
Yeah, it's dBm. It's decibel milliwatt.
Okay.
So we're still measuring power, and I like to tell people that, well, look, when we think about light, it's just really, 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 really high frequency RF. And then, of course, another perspective might be that RF is just really, 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 really low frequency light. And both definitions are actually correct. And when we measure optical power in a piece of fiber, we're measuring power, much like I just described. It's the average power, and then we could certainly express it in some flavor of watts, but there too, like trying to express signal levels in a cable TV network in voltage or amperes or even watts from a peak envelope power perspective, it's much easier to use the decibel. So in optical transmission, we do use the decibel, but instead of dBmV, it's just dBm, which is decibel milliwatts. And in this case, 0 dBm equals 1 milliwatt.
And the other thing I found interesting would be if, for instance, I have a 1 milliwatt laser for the upstream, and you have 50% OMI, optical modulation index. That laser's intensity is changing, even though you can't see it because of the wavelength. But what would you actually read with a power meter, an optical power meter? Would you read 1 milliwatt, or would you read 1.5 and 0.5?
Good question. I don't know what the optical power meters do if they're just I know that it's an average, which should take into account those variations over time. That's one of the neat things. So as the signal level or the instantaneous power varies over time, and that's one reason why we use average power for characterizing RF power most of the time. Now, certainly there are exceptions, peak power, burst power, and radar and whatnot. But in most cases, we like to use average power to characterize the power in a circuit or transmission line or whatever, because the instantaneous power is changing continuously over time. And where do you measure that continuously variable or varying power? So you measure the average power, which kind of smooths out those changes. So I don't know. I haven't played with an optical power meter in years, so that might be a fun little exercise to do.
So what I've found in my own testing over the years also would be, if I go to a fiber node and I check optical power and I see optical power coming in, that doesn't prove that is being modulated, because it is reading the average anyway. So you could have your head-end modulators turned off, but your optics are still on. So you go to the node and you're like, all right, optics is fine because I have power. But it doesn't mean the RF is being modulated. That's
right. It'd be the equivalent of measuring a CW carrier.
Yeah, exactly.
You have energy. It's just no modulation on it.
That's right. That's right.
Okay, Ron. Well, you have 10 more minutes before your next presentation. So.
Well, I need to drop to get ready for that, because I'm doing another training seminar here in now about 9 minutes. So I need to drop and get ready for that. But Brady, I want to thank you for inviting me to participate in today's Hangout session. This has been a lot of fun. These are fun, and hopefully the information that's been shared is something that folks will find useful. If people would like a copy of the PowerPoint slides that I used today, they're public domain kind of slides. I'll be glad to send a copy out. I did make a couple of minor tweaks to the slide deck I used today. That's got a couple changes that aren't in the versions that you guys have got. But I'll be glad to make this available to anybody who's interested.
Okay. Well, Ron, fantastic material. It's great having you. We'd love to have you back sometime, maybe for an RF part 2. John, great having you again. So, guys, it was a wrap. Have a great weekend, and you all take care. So, bye-bye.
All right. All right. Thanks all.
Get your taxes done.
Tax day.
They're done.
Bye-bye.